Lesson 7, Recurrence Relations. If you know how to get from one term in a sequence to the next, you can write a recurrence relation. The recurrence relation un plus 1, so the nth plus 1th term, is equal to a function of un, defines each term of a sequence as a function of the previous term. For example, the recurrence relation un plus 1 equals 2un plus 3, where u1 equals 6, will produce the sequence 6, 15, 33, 69, 141, and so on, because 2 times 6 plus 3 is 15, 2 times 15 plus 3 is 33, 2 times 33 plus 3 is 69, and so on and so forth. Let's do an example. Let's find the first four terms of A, un plus 1 equals un plus 4, where u1 equals 7, and B, un plus 1 equals un plus 4, but where the u1 equals 5. For part A, for n equals 1, we know u2 equals u1 plus 4, which is 7 plus 4, which is 11. When n equals 2, u3 will be equal to u2 plus 4, which is 11 plus 4, which is 15. And u4 will be u3 plus 4, which is 15 plus 4, which is 19. Therefore, the sequence is 7, 11, 15, and 19. For part B, we do the same thing. When n equals 1, u2 is equal to u1 plus 4, which is 5 plus 4, which is 9. When n equals 2, u3 will be equal to u2 plus 4, which is 9 plus 4, which is 13. And when n equals 3, you get u4 equals u3 plus 4, which is 13 plus 4, which is 17. Therefore, the sequence is 5, 9, 13, 17, and so on. Let's do another example. The sequence A, A1, A2, A3 is defined by A1 equals P, an plus 1 equals an squared minus 1, where n is greater than or equals to 1, and p is less than 0. Part A, let's show A3 equals p to the 4 minus 2p squared. Part B, given A2 equals 0, find p. Part C, find the sum from 1 to 200 of AR, and D, write down the value of A 199. Part A, we know A1 is equal to P. A2 will be A1 squared minus 1, which is P squared minus 1. A cubed, A3 will be A2 squared, which is P squared minus 1 squared minus 1, which is P to the 4 minus 2P squared plus 1 minus 1. And so, therefore, A3 equals P to the 4 minus 2P squared as required. For part B, given A2 equals 0, find P. We know from the first part that A2 is equal to P squared minus 1, and that is equal to 0. Therefore, P squared is equal to 1, and as P is less than 0, P cannot be equal to 1. Therefore, P equals minus 1. For part C, we know that A1 is equal to P, which is minus 1, A2 is equal to 0, A3 is equal to minus 1, and so on and so forth. And so the series alternates between minus 1 and 0. And so for the first 200 terms, there will be 100 minus 1s and 100 zeros. So therefore, the sum from r equals 1 to 200 of AR will be 100 times minus 1, which is minus 100. For part D, we need to consider the terms where for an, where n is even and n is odd. We know A1 is equal to minus 1, so when n is odd, we can see that it's minus 1. When A2 is equal to 0, we can see that if it's even, it's equal to 0. And when A3 is odd, and so we can see this is equal to minus 1. So when n is odd, we can see it's equal to minus 1, and when n is even, we can see it's equal to 0. We're trying to find A 199. 199 is odd, which means it must be minus 1. A sequence can be increasing if un plus 1 is greater than un for all natural numbers n, for all positive integers n. This means that every term is getting larger and larger as you go on, and so we say it's increasing. It can be decreasing if the next term is less than the previous term for all positive integers n, and it can be periodic if the terms are repeating in a cycle. For all periodic sequences, there is an integer k such that un plus k is the same as un for all n in the n sets, for all natural numbers n, for all positive integers n. K is called the order or the period of the sequence. Let's take these four sequences. For the first one, we can see that every term is getting larger, and so this is an increasing sequence. For the second sequence, we can see that each term, as we go on, is getting smaller. It's going from -3 to -6, -6 to -12, and -12 to -24. So this is a decreasing sequence. For the sequence -2, 1, -2, 1, -2, 1, we can see that it's repeating -2 and 1. And so this is periodic with a period of 2. Because u1 is equal to -2, and u3 equals -2, and 3 is 1 plus 2, is repeating every 2 terms. For the last one, 1, -2, 3, -4, 5, -6. It's neither increasing, because the terms aren't getting larger as you go, it's not decreasing, because the terms aren't getting smaller as you go, and it's not periodic, because none of the terms are repeating. So it's neither increasing, decreasing, or periodic. Let's do one final example. For each of these sequences, let's state if they're increasing, decreasing, or periodic, and if it's periodic, let's state the order. For part A, if we expand the first few terms of this sequence, we can see the sequence is 7, 10, 13, 16, and so on. And as un plus 1 is bigger than un, because each term is getting larger for all n, the sequence is increasing. For part B, if we expand the sequence for the first few terms, we get a half squared is a quarter squared is 1/16, 1/16 squared is 1 over 256, and so on. We can see that the terms are getting smaller every time, so therefore the sequence is decreasing. For part C, if we expand the first few terms, u1 will be sine of 90 times 1, sine of 90, which is 1. u2 will be sine of 180, which is 0. u3 is sine of 270, which is -1. u4 is sine of 360, which is 0. u5 is sine of 450, which is 1. u6 will be 0, u7 will be equal to -1. We can see that the terms repeat. We have 1, 0, -1, 0, then back to 1, 0, -1, and so forth. So therefore, the sequence is periodic with an order of, we can see the first term is 1, and then the fifth term is 1. And that's the first time, that's the first occurrence where the terms repeat. So from the fifth term to the first term, it's 4 terms. So it's every 4 terms. So it has an order of 4. And that's it.